Professor Swine has supervised two PhD programs and two other are in progress. He has also supervised 11 master dissertation. He has published several research papers in international journals and conferences as well. He is also a reviewer of several reputed international journals. So Professor Swine, he will be delivering a talk on role of CAD in product and assembly process integration. Now I request Professor Swine to please start the session. Over to you, sir.
Thank you. Nice introduction. So I will just share my PPT, but that is I'm not allowed to do so. So my PPT is visible.
Yes, sir.
Yes, sir. It's visible.
Yes, sir.
So good afternoon. Before starting the lecture, so I will speak something. Basically, my area of interest is CAD and product design. So, so basically, from in IIT Roorkee, I'm teaching CAD. I think from 2013, and prior to joining this institute, I was also as assistant professor at IIT Guwahati, and there I was teaching product design and CAD, two subjects I was teaching there. So I am assuming all attendees are teachers. So after this lecture, basically I want to say something that as a teacher, what we should teach in the subject of CAD. Maybe maybe I'll take 5 minutes. Why this is important is because while I was studying my bachelor's, I was studying something else in the name of CAD, and the same trend actually I am observing in many universities, many colleges, that in the name of CAD people teach CAM, blah blah blah, so many things. So that's why if I get the opportunity, then I'm assuming all are teachers, so at least I want to say something about that, so that at least we should deliver something which is useful to the students we are teaching. So this is the outline of my presentation. So first I'll talk about discuss about the introduction. So in the introduction I'll talk what is the motivation behind this research and what are the objectives, and then I'll discuss about the liaison, basically the assembly joint we have used as an interface between this design and this assembly process. And then we have extracted those informations, those design or those design knowledge, or design or the joint informations from the CAD model or from the assembly model. So those part also I will discuss here. So first part I will talk about the extraction of liaison associated with riveting, welding, bolt fastening, and thread fastening. And if time does permit, then I may speak something about on extraction of this adhesively bonded assembly features, like the types of joints available in adhesive bonding. Then I will talk about the integration part, where we are integrating the design or the product model with the process model, and three types of integration I will talk here. So one is basically the concurrent evolution of assembly process model, assembly process model with the product model. Then I'll talk about maintaining associativity between product model and process model. And the third type of integration, I'll talk about ontology-based approach for assembly variant design. So this is one image I have taken from internet. So that is basically one assembly scenario of one aircraft industries. And if you see this image, right, you can imagine that how complex is this process. So there are large number of machines are used, men, materials, so many things. So if you visit any automotive manufacturing, any plant, right, assembly plant, right, you will also realize similar kind of structures in the automotive sectors. Right? So in summary, it is I can I'm quoting from a very good statistics that 50% of the total production time in assembly basically accounts for 50% of the total production time, 20% of the total unit production cost, and one third of the company's manufacturing labor. Right. So so if you are not taking the decisions right during the design stage of the product, right, or if you are not taking the proper decision at the design stage of the product, then you will be having down the line you will find lot of changes during the production while you are freezing the design, after freezing the design you will find lot of changes, right? And those changes whatever the changes you are making right after the design is frozen, right, you have to pay huge amount of money for that. So that's why again one more sentence I'm some from some survey I'm saying that decisions taken during design determines 80% of the product life cycle cost. So this is basically so this research is basically our primary focus is basically assembly based industries, right? So assembly based industries means what I mean is that basically they outsource individual components to the various OEM. OEM means I'm talking about here is original equipment manufacturers, and take those equipments or components to the factory or to the assembly shop floor, and the majority of the revenue or the majority of the profit they gain by doing the assembly operations. So basically, this is a typical product development scenario where the design department designs the product, right, and they send the CAD model, right, to this data exchange or the people those who are dealing with or the department which are dealing with for outsourcing the components, right. Now they are sending this to the OEM, and they are manufacturing individual components, right? So, for example, if we are talking about automotive sectors, then there are roughly 50,000 parts. So they are sending all those 50,000 drawings. Hardly they are manufacturing little bit in their own setup, and rest of the things they are outsourcing, and they are taking that. Components, and finally they're assembling in their softwares, right? So for these companies, right, so the majority of the cost control is in the assembly operations, right? So if they are making some mistakes, right, here, right, in this design stage, right, then they have to pay a huge amount of money here, right? So a lot of changes will be there, and ultimately, production delays and also good things will be there, right? So that is why it is necessary that we have to make automation in assembly process planning, right? Now, if I say all these things, in the in our simple terms, then basically that we have to integrate the design with the process, so that at the design stage, right, we'll be able to know that if I am going to change something here, then how it will impact to my process, and all sort of process optimization. Everything has to be carried out at the design stage before sending individual component to the manufacturer. So in assembly-based industries, right? So various issues and bottlenecks are, right. So suppose if I am talking about the aircraft industries, right, then they are using multiple types of fasteners, right. So for multiple types of fasteners, right, they have multiple setups, and because they are using multiple types of fasteners because of their functional aesthetics requirements, right. So chances, majority of the time, right, the person who do the assembly operations, right, do a lot of mistakes, and those mistakes basically, it has been observed that because from the design department, the information whatever they pass to the soft floors are not precise, right, and so because of that, they have a lot of unnecessary machining they do. Even many a times they do wrong machinings, right. Many a times that in aircraft industries, right, we basically use two-sided fasteners to reduce the cost, right. But many a times that because of the two-sided fasteners, right, so we have reach or accessibility issues as opposed to the one-sided fasteners. Similarly, we have lot of problems. And if I talk about automotive sectors where they will do spot welding, they do riveting, they do bolt fastenings, right? So a lot of problems, issues they encounter, right? And the cause of these issues are not the design informations are not properly integrated with the disassembly processing. And the major bottlenecks are that the problems whatever uh, the soft floor people face, or the kind of mistakes they do, right, or so those kind of issues, right, or those kind of problems are basically discovered at the late stage in the life cycle of the product, right. And and most of the time, right, so one more major problem is that the design choices, right. So suppose whenever the designer designs something, right, so they feel that they are the supreme in the industry, and whatever the design, right, so they assume that from their experience they say that okay, this is correct, let's go ahead. I have to use this type of board. From last 10 years I am using this board, so now I will also use this, right. I am using from last 15 years this kind of process, so we are not facing any problems. So those kind of thumb rules they use many a times, right. And basically it depends upon the choice of the individual designers, right. So if you take a specific kind of joints, and if you'll ask from the same company, same group, that how will you manufacture this, right, to the designer A, right, he will say certain kind of specifications, and if you will ask to another one designer, he or she may will tell another certain kind of specifications. So you'll find a lot of variabilities, so that's why majority of the time, because of this, the choices are based on their experience, right? So we face a lot of problems. So to resolve this kind of issues, right? So we are not the first people we are doing this. So many people in the literature they are trying to address, right? So basically they are trying using concurrent engineering frameworks for product development, including your design for manufacturing and design for assembly. The second type is, specifically, I have visited many times this Boeing manufacturing setup design department, right? So what they do is they invite all the stakeholders to a common platform, right? So to a common big room, and one person will go and display the design, and he will discuss the design philosophy there, and all other will participate, and everybody will raise their hand saying that I have these issues. If you make the joint like this, I will not be able to do this. So if you will fix like this, then it will be probably difficult. And if you imagine that, there are some 50, 60 or 100 designers sitting and discussing one design, then you can imagine that how complex is the process, right? So how to and how complex to resolve all kind of issues, right? So similarly, and there are other issues also, that that now things have globalized, and you may find some design department maybe in Bangalore and manufacturing set up somewhere else, and maybe 3 4 design departments in 3 4 different places across the globe, right? So every time bringing all the stakeholders to a common goal is a really a challenge, right? So that is why NIST and other research organizations started developing these information models, right? And the first of this nature I can say is the core product model. Again, they have improved that one, saying that core product model 2, and then again they have improved as the open assembly model. Similarly, in the various universities, right? So people started working. People are working, and in the university level, the first of the system of to resolve this kind of problems is evolvable assembly systems, and in the NIST again, they have developed a process specification language, right? But in most of the approaches, if you see, right, that those are basically are developing process models, right? And those process models primarily captures the sequence information, that how in what sequence I'll put the part, I am without telling how I will join those components, right? So if I say that I have to put part A after putting the part B, but if I'm not saying that if I'll put part A, after putting the part B, and while I'll put the part B, what type of operations, right? Whether it will be welding or it will be riveting or I have to do bolt fastening. So all those things, that we are, they are not addressing, So the process description are at, very high level. And so that's why, that even though they are giving some partial solutions, but those are really not useful in real time scenarios. That is why, in summary, I can say that this traditional method of this design and manufacturing practice has adverse impact on design cycle time, lead time to market, and ultimately, it leads to the product cost, right? So basically, our goal here is exchange information, seamlessly between the design and process, and the second goal is, product model need to evolve with the process model. So, the concurrency part also we are addressing that, in detail. I'll discuss, and product and process model, we will develop some framework. So we have developed some framework, right? So that, product and process model has to be integrated in such a way that, that should be automatic. You can make, automate reasoning, right? So that, if you ask some questions, or if you have something, some changes, if you're doing in the design, then what is its impact to the process, and those kind of things, we always call this as the product and process model to automate reasoning. So basically, to do this kind of integrations, right? So we have developed, product information models, right? So we have developed product information models for basically, concurrency between product model and process model. So in detail, I will discuss associativity between product model and process model. This also I will discuss sustainability evaluation. So now that we are talking about various sustainability issues, right? So if we have integrated sustainability with this product information model. I will also talk about variant design. So variant design is a different kind of design. So that also I will talk here. And there will be fastener selection. So this sustainability evaluation and this fastener selection I will not going to cover in this presentation. And variant design I am going to cover, but if time does permit, then I may leave. If time doesn't permit, then I may leave. So I'll discuss about this associativity between product model and assembly process model, and concurrency between product model and process model. So for this integration between the this design with the process, or this design with the assembly process, right? So we have developed a framework. So that is liaison based framework. So the first part of this research is basically representation of liaison from CAD, right? So basically, that this is our own definition. So people, I know we are not the first people that we have used the word liaison. So many people in the past, basically they have used the word liaison, but for them, the liaison is basically is a simple connection or between the faces of contact. But for us, basically it is structured collection of geometric entities and connected parts in an assembly, which is associated with one or more assembly process associated with it. So now if you see, right, so you just see that this is part A and this is part B, right? So if you take these two parts, right, and if you see individually, right, for this one, right, so both the parts having 6 number of holes, right? Now if so if you put the part this way, then the joint will be basically the lap joint with chain of holes. Similarly, if you just flip the part, right? So you just see this is a different kind of joints, right? So now if I talk in terms of assembly process, right? So basically, if you want to join these two parts, then you have to do riveting operations. If you can put the bolt, right? But now if you look, just if you flip the part, then the process will be different, right? So here, you can do some sort of a gluing, or you can do some sort of a welding, right? So you just see that how simply if you will change a little bit, how things have changed. So basically, this liaison have been used, in the past to capture only what is being assembled and not the process basically used to assemble, right? So if I am saying that only these two faces are in contact, right? That we are missing the link, how to connect it with the process. So basically, actual process to realize the assembly joint is, only specified at the very high level of, abstraction. So, in the literature, people are saying that, we are just doing welding, we are just doing riveting. But, to do such kind of riveting or welding, right, you need many other, supporting process, right? So those informations are missing, right? And basically various informations available, right, are in a separate drawing sheets. We call it all those sheets as the process sheets. And since these informations are available in different places, right? So basically these informations are diffuse and not amenable for computer based reasoning. So that's why it motivates us to integrate between the design with the assembly process, which will be really required from the industry. So these are basically the information available in the literature, right? So Massel, Keel, Ulla, many people they're talking about the liaison, but the major component of the liaison they have missed. So so these kind of information, basically, this back piece, hole, location, piece, pattern, grooves, joint roots, joint radius. So all these informations were not captured whenever they are talking about the liaison. So that's why it is difficult if because many times people ask us that since all these informations people have worked, then why this type of new framework or new information models are required, right? So to answer to those questions, right, so these informations are basically not captured, which can be linked to the assembly process. Basically, various types of liaisons are available in the literature as well as in the industry. So basically, liaison associated with the welding, riveting, threaded fastening, bolt fastening, and adhesive bonding. Right. So in today's lecture, basically, that I will talk about welding, riveting, bolt fastening, and partially I will talk about the adhesive bonding. Basically various types of joints or the liaisons available, right? So basically, if you see here, right, so this is basically liaison between a pair of parts, right? So now, if you see the figure B, right, so basically this is a sub assembly between this part, right? So again, this is a liaison, right? Similarly, basically, multiple liaisons between two parts. So if you see here, this is part one and this is part two, and this is one joint here and the other joint is here. Similarly, multiple lesions of one part with different parts. So if you see here, right, so you just see that this L-shaped part is one, and now it is connected here as well as connected here. And again, in many literatures they are talking about lesion or the joint between pair of parts. But in the industry, you will find that at a single location you will find multiple parts, right? So multiple lesions at single places. So basically, you just see between these T joints and this flat plate, that is, will be one lesion, and again, the L-shaped part on the flat plate, you will find another one types of lesion. So these are the various lesion attributes. Basically, we have collected from various sources to capture the assembly joint information. So, for example, if we want to capture the welding, then we need the groove angle, root edges, root face, root gap, joint roots. Similarly, your joint shape, like U groove, V groove, J groove, right? And suppose if you want to capture the riveting, then we need the information about hole, shape, back pitch, location, pitch, hole depth, marginal pitch, etc. Right? Similarly, pattern, diagonal pitch, cover plate. So all sort of information. Basically, first that we have searched from various literatures. We have discussed with various industry people, right? And we have developed a data structure to capture all these kind of informations specifically available in welding and riveting process. So this is basically one example of lesions. We have taken, one, wing of a aircraft, right? So basically, so this is two parts I have taken. So basically, this is, spar. This is the spar, and this is reef, and this is the enlarged region. So if you see here, there are 6 holes, and similarly, this is spar 1 and reef 2, and this is the lesion, right? Now, whatever the joint information is available there, right? Those informations we are capturing here, right? So we have structured the lesion information in terms of lesion attributes such as root gap, relative surface overlap, relative orientation, relative location of parts, joint types, plate thickness of joint, similarly cross section. Again, to define cross sections, we need joint angle, joint radius, and shape of the joint. Similarly, for hole, we are to capture the whole information, we are defining shape of the hole, location of the hole, hole diameter, hole depth, whether thread informations are there or not, chamfers. Similarly, for to define a pattern of holes, we are again define certain sub attributes like marginal pitch, pitch, diagonal pitch, back pitch, pattern, and again cover plates. And whatever the two examples I have shown there, right? Both the examples, we have manually connected all the informations and wrote here, right? Now, so once these informations we have collected, right? So then we have integrated all these this data structures, whatever we have developed, right, with the niched OM architecture, so that we can uh, use whatever already developed, information model. We can use that. So that's why, we have developed this liaison data structures, and we have integrated here with this assembly feature association developed by the NIST. Then whatever the data structures we have developed, right? So those data structures we have taken and integrated in ontology development tool, that is basically one information modeling tools, right? So those tools are used in many places, right? So it is used in manufacturing, additive manufacturing. So wherever, if you want to integrate certain kind of information, right? So that is basically developed by Stanford University, and is freely available tool, and very user friendly. You can take that, and you can use that, right? So basically, we have taken all those informations, and we have taken this niche assembly feature association, and from there we have extended our data structures. So if you see, right, so whatever the parameters we have defined there, so all these parameters, is available here as cover plate, cross section, hole against, hole facing, and name of the joint, part list, pattern against, pattern facing. So all these informations we are storing. Now, again, to structure the whole information, you just see again we have defined for whole, at chamfer, diameter of the whole depth, whole feature, whole shape, location, name. So if you see the chamfer, we are storing as a float, right? So in diameter, we are storing as a float, right? So all those, location, you just see we are storing as instance, because location again, it is basically a point in the space. So it has x, y, z coordinates, and those locations again, we are defining in a separate window, and again, we are using that here. Similarly, if you see here, pattern, we are, defining as back pitch, diagonal pitch, marginal pitch, name, and pitch. And again, you'll find, some are float, some are string, and we are storing all these information. Right? Similarly, cross section, so joint angle, joint radius, name, shape of the joints, all these things. Now, that these slides basically tell us that, that why these kind of frameworks are required, because design is an iterative process, right? So whenever, I'm doing some design, right? Basically, always, I do not have complete information. As the design progresses, right, we will get many detailed information, and based on that, that process, gets freezed. So for that, that if we have partial information, we have basically, large number of processes are available, and whenever, more and more joint informations, if you are freezing, then, your process are also, gets, freezed. So basically, if you have only, root gap information, then you have, this kind of four processes. If you have, suppose if you have overlap, then these, if you have, so like this, many options you have, and these all these options, we have coded in the form of rules, in our developed ontology, and we are doing some sort of a reasoning. So basically, whatever the information I have shown there for the two examples, right? So basically, we have manually extracted, but if you see, one simple, car, right? There are 50,000 parts, and at least, you will find 2 lakh joint, right? Similarly, if you take one aircraft, right, there are, large number of parts, right? And more than 1 lakh, 2 lakh parts, right? And large number of joints, right? So manually, that if you are really talking for a industrial assembly, right? Having suppose 20 to 30 parts, right? And having 20 to 30 joints, right? So it will be really tough and challenging to extract, all kind of informations manually, and feeding those informations to the information models. So that is why that we have developed algorithms to extract all those informations, that we require for our lesion data structures. Basically, this currently, the commercial CAD systems, whatever is available, the SolidWorks, CATIA, etc., is available, right? Are not capable enough, to give us, these information automatically, right? And these informations are also not explicitly available in those CAD models. Even though that somebody may be confused with what I am saying is that you just see this is a CAD model, right? So your eye can see that okay, there are 5 holes, right? But the CAD model or the CAD software doesn't know that how many holes are there, what is the diameter of the holes, right? What is the depth of these holes, right? So these informations, because our mind is tuned, right? So that's why by looking this, we are able to know this. But the CAD model doesn't know that what is this. The CAD model only know the space what is information only is available in the CAD systems. Now, so this is simple assembly, right? So if you are doing it manually, then it is fine, right? But if you're talking about, this is basically a portion of a wing of a aircraft, right? So if I'll take, that, wing test box here, right? So we have basically 15 parts, and there are something like, you'll find something like 40 joints here, right? And manual expression, extraction of these informations are basically, this time consuming and basically error prone. And if there are a large number of parts are available and parts are complex in nature, then probably you may take months. Still the information whatever you will extract manually will not be correct. For that, we have developed a set of algorithms, and those algorithms are basically broadly classified into 2 categories. So, one set of algorithm we are basically using for identification of the lesion types or the joint types, and another set of algorithms we are using for the extraction of the features, right? So, for example, whether it is a groove or not, or if it is pattern of holes, so all sort of things are comes under the features category, right? So again, these are basically, if I combine all those things, then we have basically joint determination, determination of overlap type, then determination of joint directions, relative orientation of the joint faces, relative location of the joint faces, identification of the lesion features such as hole, cover plate, slots, identification of the lesion feature parameters, and identification of the joint shapes. So all these detailed algorithms, I'm not discussing here because each algorithm itself will take 5 to 7 minutes to discuss. So that is why I'll just whenever it is necessary, I'll talk a little bit about those algorithms. Have used basically this commercial CAD systems, SolidWorks API, and so some of these functionalities we have, functions we have used, and on the top of that we have developed certain codes, and those codes are basically implemented in VC++, and we have used very normal computers, right? So if you see here, right, this window platform, Core Studio, and some 3 GB RAM we have used. So it is not something like i7, i5, i3. Very poor systems we have used, and we were able to successfully run all those programs, right? So if you have a very simple laptops, you can do this kind of programs, and you can do a lot of research, and you can publish papers, and you can help industries. You can do a lot of consultancies. So basically, so this is a portion of a aircraft wings, right? And basically, this is the SolidWorks environment. So I have used SolidWorks environment as the visualization environments, right? And this is basically in the we have implemented in the VC++ using the SolidWorks API, and these are the informations we are extracting, and at the same time, all these informations we are writing to a file from where our ontology information model, whatever the ontology we have developed, right? It will read those informations and take it to those environments. So basically, this is there are many results, but I will show you one or two. So this is basically liaison between RIP2 and SPAR3. So if you see here, right? So if you are looking from this side, right, you can see there are two rows of holes, right? But if you see the inner portion, right, so you can see there are one portion cut is here. So that is why one line of hole is we are is here, and the other line of hole is in the bottom part. So that's why you will find because we are processing between the pairs of faces. So basically between this face and this face you will find this set of holes, and between this face and this face you will find this set of holes. And if you see here, you just see the total number of holes are 6. Center of the hole, diameter, hole shape. So everything we are capturing, we are automatically extracting from the CAD model, right? So if you imagine, right? So here basically there are 12 holes, right? But if you see a real aircraft, right, and wing, you may find there thousands of holes, and manually zoom, pan, etc. If you do, and if you measure all those things, then you can imagine how tough it is. Similarly, this is again the bottom portion, and we have extracted all these informations. This is basically the T, and this is basically enlarged portion. So we have extracted. You just see here the number of rows of holes. Again, we are extracting here pitch, pattern, back pitch. So everything we are capturing here. Similarly, this is one more capture. We are extracting here, right? This is one more example. Basically, scheme 1 and spark 3. So all this information we are writing to a file, right? But you can write to some you can store all these informations to Excel, and you can read from the Excel because now I have seen most of these integrations whatever the researchers they are using, right? So they are writing to Excel file, and from the Excel they are taking the data. So again it is convenient, right? So after joining here, right, so one of my students basically developed some frameworks where he was extracting the information from basically this additively bundled assembly, from the additively bundled assembly features, writing to Excel file, and from the Excel file again he's taking to the Proteus database. So after developing all these algorithms, we have implemented, and those algorithms basically we have computed the complexity of the algorithms. Basically, the complexity is to know the efficacy of the algorithms, right? So how efficient our algorithms are, right? So basically, efficiency is measured in terms, complexities measured in terms of big O, small O rotation. So all those things, I'm not talking because these are all computer science terms, right? So basically, that is order of n square plus order of m nf square. So here, basically, your n is your number of parts in the assembly, and m is the total number of liaisons of the joints available, and nf is the number of faces in the part. So now I'll talk about how we will use basically those use the liaison for integrating the design with the process, right? So the first sort of integration is basically concurrent evolution of assembly process model with the product model, right? So basically, you just see that whenever why this idea is a novel idea is basically, in the industry, right? So whenever we design something, right, we never thought about the process. So once the design is frozen, right, then we pass the design to the process planning group, and and you know and we ask them to design the process, right? But but what happens is, problems in design with respect to its manufacturing and assembly, right? Basically, if we follow that approach, right, then that after the design only we'll be able to find out what the assembly related issues are, right? And basically, in evolving design, right? So where the design is evolving, right? One would like to know the manufacturing implications of any decision, right? So if you are taking some decisions, right, and if you know the manufacturing implications, right, then probably you'll be careful that I should not follow this process, or I should not use this type of welding or this type of bolt fastening, right? So basically, so that is why that perhaps we are the first people who have proposed this idea. We are the first group, right? That this process model needs to evolve with the product model concurrently, right? So basically, the mistakes or the infeasibility in the process model can be flagged right away, right? So basically, that we have while developing this framework, right? We have followed the designer's working style, right? That how the designer is designing the product, right? So basically, whenever the designer designing the product, right? So basically, they start something from a simple shapes, right? So and that we so whenever the designer is designing some shape, right? Very simple shapes, we were trying to assign a certain kind of processes, right? So we were giving certain kind of some large number of process, right? We make available to the designer, saying that you just see that if you choose configuration, suppose like this, then you have a certain kind of processes. And now, suppose if you are thinking that after some stage, if your design is like this, then you have a certain set of processes. And suppose if your design will be like this, then you have a certain set of processes you have. So if you see this incremental way of the designers design activities, right? We are incrementally assigning the process information. So whenever you add more and more information, and parallelly your process will also be gets refined, right? So the moment you say that my design is frozen, then at the same moment, then I'll say that my process is also frozen, right? Basically, that so for that we have developed a assembly process library. So basically, this assembly, so we are calling that as the process model library. Basically, we have referred various process sheets, various handbooks, and we have developed this assembly process library. This assembly, this process model library, which contains, all the process required to assemble the process. And basically, that we have kept some provisions that, the process model library is expandable, in case we have missed something, then, somebody in future, if they want, they, or some new process will come, they can add it. And so basically, again, we have classified the process into three categories. One is fabrication process, the second is supporting process, and the preparatory process. So for example, right, so if I'm talking about riveting, so that is riveting is a fabrication process. So for riveting, the preparatory process is basically drilling holes. Or for suppose welding, the preparatory process may be groove cutting, right? And supporting process are basically the process which are used for basically the fabrication as well as the preparatory process for aligning the two parts, or cleaning those, so those kind of processes. We have all those processes we have classified. We have collected all those process from the industry. So for that, I have visited Boeing, I have visited our aeronautical development agencies, various automotive sectors like GM, Cleveland, TBS Motors, all those, and I have collected all those informations, and I have developed a process model library. And again, I have defined each and every process as an actuator that somebody has to do the process. To do this assembly process, one assembly joint is required, name of the process, preceding operations, succeeding operations, process constraints. To do the operations, we need a tool. So all those things, we are capturing in our process model. So this is basically we after doing this one, right? So we have basically developed a framework, right? And we are I'm telling this as the framework for concurrent evolution. So basically, if you see here, right? So we have initial product model. So product model means here I refer as the this assembly joint assembly model with a special focus to this assembly joint, and we have an initial process model, right? So basically, if I have a very simple geometry, right, based on those geometries, I have basically some sort of a process, right? And now I'm calling that as the intermediate product model and intermediate process model. And these intermediate product model and intermediate process models are basically linked, integrated with the help of the liaison, whatever we have defined, implemented, and extracted. Right? Now, if you see here, right? So if you come here, that you add some information to the liaison, right? And if yes, then again, it will come here, and again it is intermediate process model, right? This one, your liaison will be updated, and again it will come to your intermediate process model, right? And again, you add some process information, and again it will come here, right? Like this, this loop will continue, and the moment you are saying that no, I do not want any more information to the liaison, then you have a final process model, right? And for that also, we have implemented something, right? So basically, if I want to again, further elaborate the idea, right? So you just see that if I have a simple joint, then the informations are root gap, surface overlap, relative orientation of mid surface, relative location, thickness of the plates, reference age, right? And with these informations, these are the process available, right? So riveting, bolt fastening, screw fastening, blind fastening, welding, gluing, glue with rivets, right? So now suppose here basically if you add some pattern of holes, right, then you just see this welding etc. will not be available, right? So now you have riveting, bolt fastening, screw fastening, blind fastening, so all sort of things you have. Similarly, if you have now the pattern of holes, if you again expand, then you have pitch, marginal pitch, back pitch, diagonal pitch, and now you have these four informations. And now, suppose in the whole, if you add the thread information, then you have only the screw fastening. So now this is some examples here that that we have. Suppose one T joint, right? And this is the liaison. So with the T joints, we have welding and gluing, right? And now the human expert says that I want to make the joint as lab, or the designer says that no, you make this as a lab, right? So without the changing measure configurations, right? So if you just make this region as a lab region, then you have so many processes available to you. And now from here, suppose if you keep riveting, then it will ask you that whether you want to go for double row chain or double row zigzag, and based on that, your process will get refined, right? Similarly, this is one more example that if you have a corner joint, you have, three types of choices you have, right? So welding, gluing, screw fastening. Now, suppose the expert, picks, that gluing, right? Now, suppose that gluing, then some suggestions will come that that gluing is may not be feasible, right? Or some issues with this, right? Then that the liaison you have to change it to the lab, then again repeating, and this kind of things, right? So So basically, this is similar. Again, the designer has added some more information, and again, you have pitch, back pitch, diagonal pitch, marginal pitch, detail lesions, then chamfer, no chamfer. So like this, the designer keeps on adding, right? And he will, your process gets refined, right? So again, we have implemented, we have developed a system for industry use, right? So that is basically, we have used the SolidWorks API, right, for with BC++ language for extraction of the liaison attributes, and we have used the Java for implementing the concurrently evolving systems and properties for visualization. So basically, that we have taken a simple, wing box assembly, right, with very simple connection, right. Now, all this information we have extracted, right. So now, if you see here, right, so basically, this is a T joint, and the options are basically welding, screw fastening, and so gluing, right. Now, basically, again, another T joins, right? So when he's asking that, enter your choice, right? That what type of process you need, right? Now, so basically, this is a lab joint, right? And the options are riveting, welding, bolt fastening, screw fastening, gluing, all sort of options you have, right? And again, if you enter your choice as riveting, then it is asking you that please fill your number of holes, holes facing least, what is the diameter, center, so all these things. Again, once you enter all information, it's asking that whether the hole has to be chamfered or cylindrical. Like this, it will keep on prompting the designers, right? So, so basically, so these are, I'm not, explaining, right? So like this, it keeps on asking, and your process, each and every stages it gets refined, and you see that finally you are reaching with your repeating. So the second type of integration I'll talk about is maintaining associativity between product model and process model in assembly, right? So basically, this is an interesting problem. Again, I'll talk. So basically, whatever the conflicts, in the beginning I was talking about that, we are sitting in a common room, and everybody is asking that no, I don't agree with this design, I want to change this, like this, many iterations, many changes are there, right? So now, for that, this associativity, we have developed that, if you want to change something in the product model, how it will impact the process model. And if you suppose want to change something in the process, right, that instead of riveting, suppose if you are saying I want to do welding, right, so how it will impact to the design, right? So based on that, that this is one of the examples, right? So earlier we have a cylindrical hole, right, and basically process change from bolt fastening to countersunk riveting, right? Now, earlier it was bolt fastening. Now, from bolt fastening, the designer changed because of some constraints, right? This example is a real-time example from one aircraft industries, and they want to make it to countersunk riveting because of this aerodynamic shape and all sort of things, right? and and now the hole changed from rounded hole. So earlier it was a cylindrical hole, right? And now I this the holes are basically countersunk holes, right? So now you just see that earlier the plate thickness was 1 mm, but for the countersunk hole, right, the minimum plate thickness would be 1.2 mm, right? Now the design suggestion is plate thickness change from please change it from 1 mm to 1.2 mm, right? So all these things, we have implemented here, right? So we are talking here about this bidirectional associativity. So basically, change in geometry. So sometimes we will change the geometry, and you may not find the change in the liaison of the assembly joints, right? Sometimes we will not be able to change the geometry, but we will change only the joint informations, right? Similarly, you can change the joint as well as the geometry of the parts, and sometimes basically if you change the part, right, it will provide such constraints that you will not be able to do certain kind of process, do the process, right? So geometry constraints the liaison for the change, right? So for that, again, we have developed one framework, right? So where basically we have a product model. So in the product model, we are basically capturing assembly, sub-assembly, liaison information. Similarly, we have a process model, right? We have a preparatory process, assembly process, supporting process, and we have developed basically this knowledge base, right? Basically knowledge based system we have developed, right? So where we are basically, if you see, all these arrows are basically bi-directional in nature, right? So basically that we are, a product model is talking to this knowledge base. Similarly, knowledge base is talking to the product model. Similarly, a process model is talking to the knowledge base, and knowledge base is again talking to the process model, right? And we have one inference engine, and again, inference engine is integrated with your geometry computation rule base. And here, when the designer is sitting here and interacting with the product model as well as the process model. So we have, collected a large number of cases from the industry, right? But I will highlight, 5, 6 cases to give you some idea that how we have developed all these things, right? So basically, we have discussed with many designers and industry experts, right? So basically, that one case is the initial assembly situation was initial assembly is aluminum sheets and labs and with single row of holes, right? And the process is riveting. And issues with the situations is basically, that with the aluminum sheet, right, weight of the structures was heavy and need to reduce the weight of the structures, right? So one of the experts says, right, and the changes suggested is basically, change the material from aluminum to composite, right? And composite doesn't allow riveting operations, right? So basically, change suggested in the structure is use gluing instead of riveting. So like this, that this is another one cases, right? So the first case is a gluing operation requires a smooth surface without hole, right? Now the design suggestion is remove all holes, right? So issues with the situation is, strength is not sufficient to hold the two parts, right? So use rivet after gluing operations, right? So issues with the situation is, the pitch for rivet and pitch for glue with the rivets are different, right? So next suggestion is use pitch as 4 times the diameter of the rivet hole for glue with the rivet operations, right? So like this, that we have collected huge amount of knowledge. We have structured all those knowledge and we have implemented here, right? So this is another one case, I'm not discussing, right? And then, we have implemented all these things in the SolidWorks using, API, using DC++ language. We have used basically Java expert system cells for implementing rules for associativity, that if you're going to change something either in the design side or in the process side, how it will impact vice versa. Proteus for visualization and Java for integrating Proteus with the JS, right? So this is, one of the examples, whatever I have discussed, right? So basically, we have taken this same aircraft wings, right? So this is an enlarged version, right? And the plate thickness was 1 mm. So all these informations we have extracted from the CAD model, And we have you know integrated these informations in the Potis environment, right? If you see here, right, you see here that one joint, right? So the diameter of the hole is 1.24 mm, right? The hole depth is 1 mm, hole shape is circular, and these are all round holes, right? You see the pitch is 31.75, right? And all these information, right? Now, you see that it suggested earlier the whole feature was cylindrical. Now it is countersunk hole, right? Now you know that the designer has changed to countersunk holes, right? Now you see that earlier the plate thickness was 1 mm. Now the system is suggesting that you make the hole depth to be 1.2 mm, right? Now after these changes, right, if you see here, right, the number of holes was, you just see the 39, and the pitch was your 4.96, and the second rule it got fired, right? And the number of holes is again reduced to 20, and the pitch is 9.92. So like this, the things, there are 500, 600 rules, 5 to 600, right? Day by day, if we are getting new cases, we are adding this. That is why, latest I didn't check, how many rules are there, right? So like this, that we are improving our knowledge base, and we are using this. Now the last part of my talk is basically ontology based framework. So I will try to finish it in 5 to 10 minutes, right? Because already it is 4:11. So basically why variant design? So in the industry, what happens is that most of the design are basically variant design, right? So suppose you have designed something, very rarely, I can say that something new design happens, right? So they have designed something. Now some new requirements will come, and the designer will go and modify some region, something, right, and produce a new product, right? So basically, elevate designers from reproducing existing design process, and instead of if you are doing everything and designing from the scratch, then what will happen is you will need a lot of time to develop the product, and by that time you produce the product, your market, other people will launch many products, right? And basically again using the variant designs, it address individual customers or individual some group of customers, and basically enable manufacturing companies to develop individualized products based on existing mature design, right? So, if you see, right, that in the industry, right, there are people are designing every day, they are producing some products, right? So where is our role, right? So how we can help the industry, right? So we have realized that the designers who are designing the product, right, whether they are doing a fresh design, starting from scratch, or if they are doing a variant design, or they are modifying something, right? So basically, the 20% of the designer's effective time is utilized in searching and analyzing various existing design information, right? And most of the design activities they do, right, it involves basically modification and mixing and matching of existing components to produce new assemblies, right? And these changes are basically whatever the changes the designer do, right? These changes, in turn, change the assembly joints or the liaison, right? So finally, if you are changing somewhere something, right, finally you have to assemble the product, right? And to create basically variant product from the existing design by fulfilling different customer requirements, right? The designer need lot of design suggestions, right? So you cannot count, right? So if you're going to change these, some changes, like this, a lot of things has happened, right? You will realize, right? So by applying these design suggestions, there is a change in the liaison, which makes the basically this variant design a complex problem, right? So in the literature, basically, or in the industry, right, you will usually find four types of assembly variant design. So one is basically your scale-based variant design. The second is basically your module-based variant design. The third is basically your feature-based and process-based. Right. So this is basically, if you see here, this is scale-based variant design. So the handle of this component of this teapot, right, is earlier of this size, now of this size. Now the types of assembly, whatever you are using here, right? So the region of overlap has reduced, right? So now based on that, the process may change, may not change, right? Similarly, if you the second type is basically module based, right? So basically, you are going to change some architecture of the product, right? So earlier it was an integral architecture. Now, if you see, this is a modular architecture, so two different components, right? Uh, Similarly, that if you see here feature-based design, right? So basically change in features. So earlier you have a board joint, and change from board joint to cylindrical snap fits, and due to need of changing a permanent joint to a mechanical interlocking joint, right? So some issues. So that's why this is basically a feature-based design. And the fourth type is basically a process-based design. So you are not going to change the components drastically, but you are just changing some process, right? So basically increase the strength of the adhesive under joint by applying spot weights, right? So these are four types of basically variant designs we are talking. So this is again, one of my PhD students has developed this framework, right? So for this ontology-based approach. So basically, he has again extracted this adhesively bonded assembly features, right? He has again, used the liaison framework for riveting, welding, bolt fastening. But in the earlier, we have not addressed for this adhesive bonding. So he has developed algorithm to extract liaison information from the adhesive bonding. So those part, I'm not covering here. So from the 3D model, he's extracting all these informations, again integrating with riveting, welding, bolt fastening, right? Then he has developed a DSSBD ontology, right? So in this DSSBD ontology, right? So he's capturing basically the customer's information, right? So customer requirements, is converting those customer requirements into the design requirements, right? So customer says that I want, the power of the engine should be high, or the customer says that the loading capacity of the vehicle should be high, or the customer says that the aesthetics of the product should be like this. So all those informations basically the variant design addresses most of the customer requirements. So all those things we are capturing here, and we have developed a uh, you know uh, decision support system for variant design. So DSSBD stands for decision support systems for variant design. So we have developed, right, and we are the output of this system is basically design suggestion needed, effect from each design suggestion on the joint information, and the variant design type require these three types of things we are extracting, and we have published this work in the ASME transactions. You can refer on the work. Um, so basically, to develop this framework, so we have basically, three types of layer. He has classified the knowledge in three layers. So basically, one is the foundation ontology layer. So he's capturing product family, product process, material, product variants, features, all these things. Then product design domain, assembly, and process planning domain, and then he's integrating all these things for assembly variant design. So this is again, he has used protease. So all these classes he has structured here like customer requirements, degree of freedom, design suggestions, like this, all these things, he's specifying, right? Then we are modeling all these information, this causal relationship between all these classes of the information, right? So, for example, product variant has a customer requirements, product family has a product variant. So like this, we are capturing all these informations, right? We are mapping all these informations. Then we wrote in the knowledge whatever we have gathered, right? We have developed in the SWRL rule. So this semantic web rule language we have used, right, to structure all those to write all those rules, right. Similarly, this mapping among core concepts. So previous one is mapping among core concepts. This is again some rules, right. So this is basically that giving us specific design suggestions, right. Then again the effect of design suggestions on features or joint information. So there are many rules, but to give you some flavor, I just wrote very few. So then again, we have some queries, right? That we wrote two queries, and these two queries, whenever these two queries fires, right? So we will find all sort of results, right? So again, we have taken on case studies, right? So chassis of an automotive assembly, and you just see that the customer requirements here, something, right? So high loading capacity, right? Now again, so this is basically two slides. So if you see here, from there it is coming that these are the outputs, right? So we need design suggestion. Again, required variant design types, all these things it is coming here, right? And then lot of process it is happening, and we are finding out that this is a basically process based variant design we are finding out. So this is some of the screen captures of our implementations, right? After doing this, we have evaluated the efficacy of the ontology, and this DSSBD ontology is measured in terms of precision, recall, and measures, right? And we are getting 79.3. So in the literature we have seen that if you are getting more than 60 to 65%, then it is a very good ontology. And these are some of the conclusions. So basically, so I'm not going into the details, right? So we have also some of the future works. If anybody is interested, they can continue this work for their PhD problems, right? Thank you. So anybody has any questions, please.
Thank you, sir, for a informative session. So I can see in the chat box there is one question from Dr. Pramod Kumar. So the question is, what are the underlying principles and factors that influences any decision to be cost saving or costly?
Could you please repeat once again?
Uh, the question is, what are the underlying principles and factors that influences any decision to be cost saving or costly?
So basically, there are a lot of things. Basically, it affects. Basically, like suppose presently in the industry, most of the cost incurred is that if they are doing some wrong decisions, and and they are not identifying at the in the design stage, and at the manufacturing or production stage, it is the decisions they have realized that it is wrong something, and again whenever they are rectifying that, then they have to redesign everything, and they have to change all components. Then they have to change this manufacturing setup. So everything that suppose if you have made some contracts. For example, I'm giving one simple example that Boeing 787, right? So they were supposed to deliver in 2008, but and they have taken the orders from Air India and many other countries, and they were not able to deliver because there were some issues, right? And to fix that issues, it took a lot of time, and for that they have paid huge amount of money. So like this, there are many factors influence the product cost.
Thank you, sir. Hope it is clear. So there is one more question from Dr. Pramod Kumar. What is the priorities in the design process, considering cost, strength, durability, reliability, ease of use, and aesthetics? What is the priorities in the design process, considering all these factors?
So basically, that it depends upon your requirements, right? So, for example, if I am talking about, again, it depends upon the customers, right? So suppose if there is a product, right? So I'm looking, suppose only aesthetics of the product, right? And that how I'm not looking about suppose the strength part, right? So I'm just talking about that the product has to look better, right? Then if the product is is satisfy my requirements, functional requirements, then I'll just say that basically that so many factors he has asked, right? So I can say in one line I can answer this is that it again depends upon the customers, right? So what the customer wants, right? Uh, so the same car is available in 5 lakhs, and if you add a little bit some more features, the cost will go up, right? So basically that it depends how what is your requirements. Because that if the product is not functioning properly, then all other factors is immaterial. So once if your product is functioning right, then the next part is that whether you are looking for aesthetics part, or or cost, or any other things, whatever you are looking, that that part will come into play.